Welcome to Network Connectivity Center. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation series, we are going to explore Google Cloud Network Connectivity Center, specifically focusing on how to use third-party network virtual appliances, or NVAs, to establish connectivity between external sites and your virtual private cloud, or VPC, network resources. This is a powerful capability that enables hybrid and multi-cloud networking scenarios. Network Connectivity Center is Google Cloud's centralized connectivity management hub that uses a hub-and-spoke architecture. Think of it as the central nervous system for your network connections, where the hub serves as the management point and spokes represent various connection types including VPN tunnels, cloud interconnect attachments, and Router Appliance instances. The Router Appliance feature is particularly interesting because it allows you to bring your own network virtual appliance, NVA, into Google Cloud and use it as the backing resource for a network connectivity center spoke. This means you can leverage familiar third-party solutions from vendors you already trust while integrating them seamlessly into Google Cloud's networking fabric. Throughout this presentation, we will walk through the concepts, architecture patterns, and step-by-step configuration procedures to help you implement Router Appliance connectivity in your own environment. Whether you are connecting on-premises data centers or linking multiple VPC networks through a firewall appliance, the techniques covered here will give you the foundation you need. Site-to-cloud connectivity pattern. Now let us examine the first major use case for Router Appliance, which is connecting an external site to a VPC network. This is the classic hybrid connectivity scenario where you need to establish communication between your on-premises data center and your Google Cloud resources. In this topology, a Router Appliance instance serves as the backing resource for a network connectivity center spoke. The Router Appliance instance has a dual role. On one side, it connects with a peer router in your on-premises network, typically over a VPN tunnel or dedicated interconnect. On the other side, it peers with a cloud router within your VPC network. The magic happens through BGP route exchange. RAWs from your on-premises network are dynamically exchanged with the VPC network. This means when a new subnet is added on-premises, the Router Appliance can automatically advertise it to Google Cloud. Similarly, when you create new subnets in your VPC, those RAWs can be advertised back to your on-premises infrastructure. Let me walk through the site-to-cloud architecture diagram in detail. The flow begins with your on-premises network, which represents your existing data center or office location that contains servers, applications, and other resources you need to connect to Google Cloud. The on-premises network connects to the Router Appliance instance through a secure tunnel, which could be an IPsec VPN or a dedicated interconnect link depending on your requirements. The Router Appliance instance sits inside your VPC network and acts as the bridge between on-premises and cloud environments. This virtual machine runs your chosen network virtual appliance software. From the Router Appliance instance, there is a BGP peering connection to the cloud router. This BGP session is where routes are exchanged dynamically. The cloud router is Google's managed service that receives routes from the appliance and installs them into the VPC routing table. The cloud router connects to your VPC resources, which are the Compute Engine virtual machines, GKE clusters, Cloud SQL instances, and other workloads running in your VPC that need to communicate with on-premises systems. The bidirectional arrows throughout the diagram indicate that traffic and route advertisements flow in both directions, enabling full connectivity between the two environments. VPC-to-VPC connectivity pattern. Another powerful use case for Router Appliance is establishing connectivity between VPC networks without involving an external site at all. This VPC-to-VPC topology is particularly valuable when you want to route traffic between VPC networks through a network virtual appliance for security inspection, traffic optimization, or policy enforcement. Consider a scenario where you have a firewall appliance that you want to use for inspecting all traffic between your application VPCs. Rather than using VPC peering, which provides direct connectivity without inspection, you can route traffic through the Router Appliance. This gives you visibility and control over inter-VPC communication. In this topology, the virtual machine that hosts the Router Appliance instance has interfaces in both VPC networks. Each interface is used to create a Router Appliance spoke. The Router Appliance instance engages in BGP peering sessions with cloud routers in both networks. Through these sessions, each cloud router learns the subnet ranges from the other VPC network via the Router Appliance. Let me walk through the VPC-to-VPC connectivity diagram in detail. Virtual Machine A represents a workload in VPC Network A that needs to communicate with resources in VPC Network B. The subnet 10.1.3.0/24 shows the IP address range for the subnet where Virtual Machine A resides. Virtual Machine A sends traffic destined for VPC Network B, and that traffic follows the route that points to the Router Appliance. The Router Appliance sits in the middle with interfaces in both VPC networks. This is where your firewall or other network function runs. All traffic between the two VPCs passes through this appliance. Cloud Router A is in VPC Network A and maintains BGP peering sessions with the Router Appliance. Through these sessions, it learns about the 192.168.10.0/24 subnet from VPC Network B and installs that route. Cloud Router B performs the same function in VPC Network B, learning about the 10.1.3.0/24 subnet from VPC Network A. The subnet 192.168.10.0/24 shows the IP address range for VPC Network B. Virtual Machine B represents a workload in VPC Network B that can now communicate with Virtual Machine A. Traffic flows through the Router Appliance in both directions, allowing your network virtual appliance to inspect, filter, or modify traffic as needed. Prerequisites and project setup. Before we dive into the configuration steps, let us make sure you have all the prerequisites in place. Proper preparation is essential for a smooth deployment of Router Appliance connectivity. The first step is to create or select a Google Cloud project. All Network Connectivity Center resources, including hubs, spokes, and the underlying infrastructure, will reside in this project. If you are new to Google Cloud, you can create an account and receive free credits to experiment with these services. You need appropriate identity and access management permissions to work with Network Connectivity Center. To select an existing project, you just need to have been granted a role on that project. To create a new project, you need the Project Creator role, which contains the Resource Manager.projects.create permission. Make sure billing is enabled for your project, as Network Connectivity Center and the underlying compute engine resources incur charges. You should also have the Google Cloud command line interface installed and initialized, as many operations are easier to perform from the command line. Let me explain the project setup workflow diagram. The flow begins with the Create or Select Project step, which is your entry point where you decide whether to use an existing project or create a new one. From there, you proceed to verify billing, which confirms that billing is enabled because Network Connectivity Center resources have associated costs. Next comes Install Google Cloud CLI, which installs the G-Cloud command line tool that you will use for many configuration tasks. The Initialize G-Cloud CLI step runs G-Cloud init to authenticate and set your default project. Set Project ID configures the CLI to work with your specific project. Finally, Enable Network Connectivity API activates the API that Network Connectivity Center requires. You cannot create hubs or spokes until this API is enabled. Each step flows into the next, creating a sequential setup process that ensures all prerequisites are met before you begin the actual deployment. Understanding IP address requirements. IP addressing is a critical aspect of Router Appliance configuration that requires careful planning. The way you configure IP addresses affects BGP peering, which is the foundation of route exchange between your appliance and cloud router. To set up a Router Appliance instance, you must establish BGP peering between the instance and the cloud router. A key requirement is that the virtual machine must use an RFC 1918 internal IP address, RFC. RFC 1918 defines the private IP address ranges that are commonly used for internal networks. RFC 1918. You cannot establish BGP peering if the virtual machine uses a different type of address such as a public IP address. Additionally, both the Router Appliance instance and the cloud router interfaces must be in the same region. BGP peering is regional, so you cannot peer a Router Appliance in US Central 1 with a cloud router interface in Europe West 1. Google strongly recommends using static internal IP addresses for your Router Appliance instances. With a static address, the IP remains constant even if the virtual machine is stopped and restarted. If you use an ephemeral address, the IP could change during a reboot, which would cause BGP peering to fail because the cloud router would be trying to peer with the old address. You have several options for assigning static IPs addresses. You can reserve the IP address in advance before creating the virtual machine. Alternatively, you can reserve the IP address at the time you create the virtual machine. If you accidentally create a virtual machine with an ephemeral address, you can convert that address to a static address after the fact. For the cloud router side of the peering relationship, the router also uses RFC 1918 internal IP addresses to peer with the Router Appliance instance. The cloud router needs two interfaces for redundancy, and each interface uses a separate IP address. These addresses can be manually assigned or automatically allocated from the subnet that contains both the Router Appliance interface and the cloud router interfaces. Creating VPC networks. With the prerequisites complete, we can now begin creating the infrastructure components. The first step is to create the VPCs networks that will host your Router Appliance instance and the resources that need connectivity. For the sample configuration we are building, you need two VPC networks. These networks will be called Network A and Network B. The Router Appliance instance will have interfaces in both networks, enabling it to bridge connectivity between them. A critical configuration setting for these VPC networks is the dynamic routing mode. You must set each network's dynamic routing mode to global. This setting enables cloud routers in any region to learn and advertise routes to all other regions in the network. For Router Appliance scenarios, especially those involving cross-region failover, global routing mode is essential. When you create a VPC network, you also specify the subnet mode. For Router Appliance deployments, you should use custom subnet mode rather than auto mode. Custom mode gives you control over the IP address ranges used in each subnet, which is important for avoiding conflicts with on-premises address spaces. Let me walk through the gcloud command for creating a VPC network. The command is gcloud compute networks create followed by the network name. The gcloud compute networks create portion invokes the network creation function. Name is a placeholder that you replace with your actual network name, such as Network A or Network B. The --subnet mode custom flag specifies that you want to create a custom mode VPC network. With custom mode, you manually create subnets and define their IP ranges. This is the recommended approach for production environments where you need precise control over your IP address plan. The --BGP routing mode global flag sets the dynamic routing mode to global. This is essential for Router Appliance deployments because it ensures that routes learned by cloud routers are distributed across all regions in the VPC network. Without global routing mode, routes would only be available in the region where they were learned, limiting your ability to achieve cross-region connectivity. Creating subnets. After creating the VPC's networks, the next step is to create subnets within each network. Subnets define the IP address ranges that will be used by resources in each VPC, including the Router Appliance instance itself. For the sample configuration, you will create one subnet in Network A and one subnet in Network B. The Router Appliance virtual machine will have network interfaces in both of these subnets, and the cloud router interfaces will also be in these same subnets since BGP peering requires the peers to be in the same subnet. When planning your subnet IP ranges, consider your on-premises address space to avoid conflicts. The sample configuration uses 10.1.3.0/24 for subnet A in Network A and 192.168.10.0/24 for subnet B in Network B. These are common RFC 1918 private address ranges that should work well for most environments. Let me walk through the gcloud command for creating a subnet. The command is gcloud compute networks subnets create followed by the subnet name. The gcloud compute networks subnets create portion invokes the subnet creation function. The -- network equals network flag specifies which VPC network this subnet belongs to. You replace network with the actual network name, such as network A or network B. The -- region equals region flag specifies the Google CP region where the subnet will be created. For the sample configuration, this is US Central 1. The subnet must be in the same region as where you plan to deploy the Router Appliance instance. The -- range equals range flag defines the IP address range for the subnet insider notation. For subnet A, this would be 10.1.3.0/24. which provides 254 usable IP addresses. For subnet B, this would be 192.168.10.0/24. Router Appliance Virtual Machine Creation Command. Let me explain the gcloud command for creating the Router Appliance virtual machine in detail. This is a more complex command than what we have read so far because it includes multiple configuration options for the network interfaces, IP forwarding, and machine type. The command begins with gcloud compute instances create followed by instance_name, which you replace with your actual virtual machine name such as Router App A. The -- project equal operator project flag specifies the Google Cloud project where the virtual machine will be created. You replace project with your project ID. The -- zone equal operator zone flag specifies the zone within the region where the virtual machine will be deployed. For US Central 1 region, this might be US Central 1-A, US Central 1-B, or another zone in that region. The -- machine type equal operator machine_type flag specifies the compute resources for the virtual machine. Common choices include N1 Standard 2 for a balanced configuration with 2 vCPUs and 7.5 GB memory, or larger machine types for higher throughput requirements. The -- network tier equal operator network_TIER flag should be set to premium. This ensures traffic between your virtual machine and other Google Cloud resources or external destinations uses Google's high-performance global network backbone rather than public internet routes. The -- network interface flag is where you configure the virtual machine's network interfaces. You specify the subnet and can optionally specify the private IP address. In the example, the syntax shows subnet equal operator subnet, private network IP equal operator internal IP address. You need to include this flag multiple times for multiple network interfaces, once for each interface. The -- can IP forward flag is critical. This enables IP forwarding on the virtual machine, which allows it to route packets that are not destined for its own IP addresses. Without this flag, the virtual machine cannot function as a router appliance. The -- image project equal operator image_project flag specifies the project that contains the appliance image you want to use. For partner images, this would be the partner's project. For Debian, it would be Debian Cloud. The -- image equal operator image flag specifies the actual image name to install on the virtual machine. This should be the image for your chosen network virtual appliance. Creating the Network Connectivity Center Hub. With the VPC's networks, subnets, virtual machines, and firewall rules in place, we can now create the Network Connectivity Center resources. The first resource to create is the Hub, which serves as the central management point for your network connectivity. A Network Connectivity Center Hub is a global resource that aggregates spokes representing various types of network connections. Think of the hub as the control plane for your network connectivity, while spokes are the data plane connections that carry actual traffic. Before you can create any spokes, including Router Appliance spokes, you must first create a hub. All spokes are attached to a hub, and the hub provides the logical grouping that enables route exchange between the connected resources. Let me walk through the G-Cloud command for creating a hub. The command is G-Cloud Network Connectivity Hubs create followed by hub name, which you replace with your desired hub name. The -- description equal operator description flag allows you to provide optional text that describes the purpose of the hub. This is helpful for documentation and organization, especially when you have multiple hubs. The -- labels flag allows you to attach key value pair labels to the hub. Labels are useful for organizing and filtering resources. The syntax is key equal operator value, where you replace key and value with your actual label text. After creating the hub, you can verify it was created successfully by using the G-Cloud Network Connectivity Hubs describe command, which shows the details of the specified hub including its state, associated spokes, and other properties. Sample spoke creation commands. Let me show you the complete commands for creating both Router Appliance spokes in the sample configuration. These commands demonstrate how to reference the Router Appliance instance by its Network A and Network B interfaces. The first command creates spoke A. The spoke name is spoke A, and it is attached to the hub called My Hub. The description indicates this is the first test spoke. The Router Appliance flag specifies the full resource path to the Router App virtual machine, along with the IP address 10.1.3.8, which is the interface in Network A. The region is set to US Central 1. The second command creates spoke B. The spoke name is spoke B, also attached to My Hub. The Router Appliance flag again specifies the Router App virtual machine, but this time with the IP address 192.168.10.3, which is the interface in Network B. The region is the same, US Central 1. Notice that both spokes reference the same virtual machine, Router App A, but different IP addresses. This is the key to enabling the single Router Appliance to bridge two VPC networks. Each spoke represents one interface of the appliance, and each spoke will have its own set of BGP peering sessions with the cloud router in that network. After running these commands, you can verify the spokes were created by using G-Cloud Network Connectivity Spokes Describe or by viewing them in the Google Cloud Console under the Network Connectivity Center page. Creating Cloud Router Interfaces. After creating the cloud routers, you need to create interfaces on each router for BGP peering with the Router Appliance instance. For redundancy, you should create two interfaces on each cloud router. This ensures that if one BGP session fails, the other can continue exchanging routes. The cloud router interfaces must be in the same subnet as the corresponding Router Appliance interface. If you are peering Cloud Router A with the Router Appliance interface in subnet A, then the cloud router interfaces must also be in subnet A. Each interface uses an RFC 1918 internal IP address from that subnet. Let me walk through the G-Cloud command for creating the first cloud router interface. The command is G-Cloud compute routers add interface followed by router name, which is the name of the cloud router you are updating. The -- interface name equal operator first interface name flag specifies a name for this interface. Common naming conventions include interface-0 or Router Appliance interface-0. The -- IP address equal operator first interface IP address flag specifies the internal IP address for this interface. If you do not specify a value, Google Cloud will attempt to find a free address in the subnet's primary IP range. For predictability, it is better to specify the address explicitly. The /subnetwork equal operator subnet flag specifies the subnet that contains this interface. The interface IP address must be within this subnet's IP range. The /region equals region flag specifies the region, which must match the cloud router's region. For the second interface, you use the same command but with a different interface name, different IP address, and you add the redundant interface equals first_interface_name flag. This flag links the two interfaces together as a redundant pair, which is important for high availability configurations. Sample Cloud Router Interface Commands. Let me show you the complete commands for creating the redundant interfaces on both cloud routers in the sample configuration. For Cloud Router A, the first command creates interface 1 with IP address 10.1.3.14 in subnet A. The second command creates interface 2 with IP address 10.1.3.15, also in subnet A. The second command includes the redundant interface flag pointing to interface 1, establishing them as a redundant pair. For Cloud Router B, the commands follow the same pattern, but use addresses from subnet B's range. Interface 1 uses IP address 192.168.10.14, and interface 2 uses 192.168.10.15. Again, the second interface references the first as its redundant interface. The IP addresses used for the cloud router interfaces must not conflict with any other resources in the subnet, including the Router Appliance instance itself. In the sample configuration, the Router Appliance uses 10.1.3.8 in subnet A and 192.168.10.3 in subnet B, so the cloud router interface addresses of 10.1.3.14, 10.1.3.15, 192.168.10.14, and 192.168.10.15 do not overlap. After creating the interfaces, each cloud router has two interfaces in its respective subnet, ready to establish BGP peering sessions with the Router Appliance instance. The redundant interface configuration ensures that even if one interface experiences issues, the other interface can maintain the BGP session and continue route exchange. Configuring Border Gateway Protocol peering on cloud routers. With the cloud router interfaces created, the next step is to configure BGP peering between the cloud routers and the Router Appliance instance. For each interface on the Router Appliance, you must create two BGP peering sessions, one for each cloud router interface. This provides redundancy so that if one session fails, the other can maintain connectivity. In the sample configuration, you will create two peering sessions between Cloud Router A and the network interface of Router App A. Similarly, you will create two peering sessions between Cloud Router B and the network B interface of Router App A. This results in a total of 4 BGP peering sessions across the deployment. Let me walk through the gcloud command for adding a border gateway protocol peer to a cloud router. The command is gcloud compute routers add border gateway protocol peer followed by name, which is the cloud router name you are updating. The /peer name equal operator PEER_NAME flag specifies a name for this BGP peering session. Use a descriptive name that indicates which Router Appliance instance this peer connects to. The /interface equals interface flag specifies which cloud router interface this BGP peer uses. This corresponds to one of the interfaces you created in the previous step. The /peer IP address equals PER_IP_ADDRESS flag specifies the internal IP address of the Router Appliance instance. This is the address that the cloud router will use to reach the appliance for BGP communication. The double-peer ASN equal operator peer_ASN flag specifies the autonomous system number of the router appliance. This ASN is configured on the appliance itself and must match what you specify here. Use a private ASN from the RFC 6996 range. The double-instance equal operator RAWTER_appliance flag specifies the virtual machine that is acting as the router appliance instance. This links the BGP peer configuration to the specific appliance. The double-instance zone equals router_appliance_zone flag specifies the zone where the router appliance virtual machine is located. The double-region equals region flag specifies the region, which must match the cloud router's region. Sample BGP peering commands for Cloud Router B. The commands for Cloud Router B follow the same pattern but target the router appliance interface in Network B. These commands establish two border gateway protocol sessions between Cloud Router B and the router appliance instance through the Network B interface. The first command creates a BGP peer named Router Appliance BGP peer Router App A0 on Cloud Router B. This peer uses Router Appliance Interface 0, which is the first interface on Cloud Router B. The peer IP address is 192.168.10.3, which is the router appliance's internal IP address in Subnet B. The peer ASN is 65001. The same as the router appliance's ASN. The instance reference points to the same router app a virtual machine. The second command creates the redundant BGP peer named Router Appliance BGP peer Router App A1. This peer uses Router Appliance Interface 1 on Cloud Router B and also peers with the 192.168.10.3 address of the router appliance. After running all four Border Gateway Protocol peer commands, 2 on Cloud Router A and 2 on Cloud Router B, you have established the complete Border Gateway Protocol peering configuration from the Cloud Router side. The router appliance now needs to be configured to complete its side of the Border Gateway Protocol sessions. Configuring Border Gateway Protocol on the router appliance instance. The final step in establishing connectivity is to configure Border Gateway Protocol on the router appliance instance itself. This step varies depending on which network virtual appliance image you are using. Each vendor has their own interface and configuration syntax for Border Gateway Protocol. The general concepts are the same across all appliances. You need to configure the appliance's local ASN, which in the sample configuration is 65001. You need to configure BGP neighbors for each cloud router interface IP address. And you need to specify which networks or prefixes the appliance should advertise to its BGP peers. If you are using a partner solution from a supported Network Connectivity Center partner, refer to the vendor's documentation for specific configuration steps. Many partner solutions provide automated or guided configuration that simplifies this process. If you are using a custom appliance, you need to configure BGP manually. The appliance must be able to accept incoming BGP connections on TCP port 179 from the Cloud Router Interface IP addresses. The appliance should establish neighbor relationships with each Cloud Router interface. Let me explain the appliance configuration workflow diagram. The process begins with Configure Local ASN, where you set the appliance's autonomous system number to 65001 or your chosen ASN. This ASN must match what you specified in the Cloud Router BGP peer configuration. Next is Add BGP Neighbors, where you add each Cloud Router interface as a BGP neighbor. For Cloud Router A, you would add neighbors 10.1.3.14 and 10.1.3.15. For Cloud Router B, you would add neighbors 192.168.10.14 and 192.168.10.15. Then comes Configure Route Advertisement, where you specify which networks the appliance should advertise to its BGP peers. This might include on-premises network prefixes or other networks reachable through the appliance. Finally, Verify sessions checks that all BGP sessions transition to the established state, confirming that route exchange is working correctly. Understanding route exchange. With BGP sessions established, let us understand how routes are exchanged between the cloud routers and the Router Appliance instance. This route exchange is the mechanism that enables connectivity between your VPC networks and any external networks reachable through the appliance. When the Router Appliance advertises routes to the cloud router, those routes are installed in the VPC network's routing table. For example, if the Router Appliance advertises the 10.0.0.0/8 prefix representing your on-premises network, the cloud router installs a route for 10.0.0.0/8 pointing to the Router Appliance instance. Now, virtual machines in the VPC can send traffic to 10.0.0.0/8 addresses, and that traffic will be routed to the appliance. Similarly, the cloud router advertises VPC subnet routes to the Router Appliance. The appliance learns these routes and can forward them to other BGP peers, such as an on-premises router. This enables on-premises systems to read resources in the VPC network. Let me explain the route exchange diagram in detail. The diagram shows the bidirectional flow of route information through the BGP sessions. The Cloud Router component represents the managed Google Cloud Router service. It maintains the VPC routing table and participates in BGP sessions. The arrow labeled VPC routes flows from the Cloud Router to the Router Appliance. This represents the Cloud Router advertising the VPC subnet prefixes, such as 10.1.3.0/24 and 192.168.10.0/24, to the Router Appliance. The Router Appliance component represents your network virtual appliance virtual machine. It receives VPC routes and can redistribute them to other routing domains. The arrow labeled external routes flows from the Router Appliance to the Cloud Router. This represents the appliance advertising routes from external networks, such as on-premises prefixes or routes from other cloud environments. The VPC routing table receives the routes learned from the appliance and makes them available for packet forwarding. Virtual machines in the VPC use these routes to determine where to send their traffic. The external networks block represents any networks reachable through the Router Appliance that have been advertised via BGP. Useful verification commands. Let me provide some specific commands you can use to verify your Router Appliance deployment. These commands help you check the status of resources, routes, and connectivity at each layer of the configuration. The first command is gcloud compute routes list with a filter for the network. This command lists all routes in the specified VPC network. Look for routes with a next hop instance pointing to your Router Appliance virtual machine. These are the routes that will send traffic through the appliance. The second command is gcloud compute routers get status for checking the cloud router status. This shows the BGP peer states and learned routes. The output includes the state of each BGP session, whether it is established or in another state, and the number of routes learned from each peer. The third command is gcloud network connectivity spokes describe for checking the spoke status. This shows whether the spoke is active and if there are any issues with the Router Appliance attachment. For network level testing, you can SSH into a virtual machine in your VPC and run ping commands to destinations that should be reachable through the Router Appliance. If ping works, basic connectivity is established. You can then run traceroute to see the path packets take and verify they traverse the appliance. If you have access to the Router Appliance's management interface, you can also check the routing table and BGP neighbor status directly on the appliance. This provides visibility into what routes the appliance has learned and is advertising. Troubleshooting common issues. Let me share some common issues you might encounter when deploying Router Appliance connectivity and how to troubleshoot them. Understanding these issues can save significant time when debugging problems. The first common issue is BGP sessions not establishing. If your BGP sessions remain in idle or active state instead of established, Check several things. Verify that firewall rules allow TCP port 179 traffic between the cloud router interfaces and the router appliance. Confirm that the IP addresses in your BGP peer configuration match the actual interface addresses. Ensure the router appliance is configured to accept BGP connections from the cloud router IP addresses. The second common issue is no routes being learned. If BGP sessions are established but no routes appear, the router appliance may not be configured to advertise routes. Check the appliance's BGP configuration to ensure it is advertising the expected network prefixes. Also verify that any route filters or policies on the appliance are not blocking route advertisements. The third common issue is asymmetric routing. If traffic takes different paths in each direction, you may experience connectivity issues, especially with stateful firewalls. Review your routing configuration to ensure traffic flows symmetrically through the appliance in both directions. The fourth common issue is IP forwarding not enabled. If the router appliance virtual machine cannot forward packets, verify that IP forwarding was enabled when the virtual machine was created. You can check this in the virtual machine details page or by describing the virtual machine with G-Cloud Compute instances describe. Site-to-site data transfer. An important feature to understand when working with router appliance is site-to-site data transfer. This setting controls whether traffic can flow between spokes attached to the same network connectivity center hub. When site-to-site data transfer is enabled for a spoke, traffic from that spoke can be exchanged with other spokes attached to the same hub. This is useful for scenarios like cross-region failover, where you need traffic to be able to read any available router appliance instance regardless of which region it is in. When site-to-site data transfer is disabled, traffic from that spoke can only reach VPC network resources. It cannot transit through the hub to reach other spokes. This is appropriate for simpler deployments where you only need connectivity between the router appliance and the local VPC network. For the sample VPC-to-VPC or basic site-to-cloud configurations we discussed, site-to-site data transfer should be set to false. For more complex deployments involving multiple router appliances across regions with failover requirements, site-to-site data transfer should be set to true. Let me walk through the site-to-site data transfer diagram. The diagram shows two scenarios. In the first scenario, site-to-site data transfer is disabled. Spoke A connects to the hub, but traffic from Spoke A can only reach the VPC network, shown by the arrow from Spoke A, through hub to VPC network. There is no path to Spoke B. In the second scenario, site-to-site data transfer is enabled. Spoke A connects to the hub, and now traffic can flow both to the VPC network and to Spoke B. The hub facilitates this transit by allowing spokes to exchange traffic with each other, not just with VPC resources. Monitoring and logging. Effective monitoring and logging are essential for maintaining healthy router appliance deployments. Google Cloud provides several tools and metrics to help you understand the state of your connectivity. Cloud monitoring provides metrics for cloud routers, including BGP session status, route counts, and traffic statistics. You can create dashboards to visualize these metrics and set up alarms to notify you when issues occur, such as when a BGP session goes down. Cloud logging captures events related to your network connectivity center resources, including hub and spoke creation, updates, and deletions. You can also enable flow logs on your VPC subnets to capture information about traffic flowing through the network, which helps with troubleshooting and security analysis. The router appliance virtual machine itself typically provides its own monitoring and logging capabilities. Network virtual appliances often include built-in dashboards, simple network management protocol support, and syslog output. Integrate these with your existing monitoring infrastructure for a complete view. Let me walk through the monitoring architecture diagram. The flow begins with Cloud Router Metrics, which provides data on BGP session state, route counts, and interface statistics. This data flows to Cloud Monitoring, which is Google Cloud's monitoring service that collects and stores metrics. From cloud monitoring, you can create dashboards for visual representation of metrics and alarms that notify you when thresholds are breached. Simultaneously, NCC events representing hub and spoke changes flow to cloud logging, which is Google Cloud's logging service. Cloud logging feeds log analysis for troubleshooting and audit purposes. The Router Appliance virtual machine also sends its own logs and metrics, which can be collected via Ops Agent and forwarded to cloud monitoring and cloud logging for unified visibility. Cost considerations. Understanding the cost structure of Router Appliance deployments helps you plan your budget and optimize your spending. Several components contribute to the overall cost. The first cost component is the compute engine virtual machine running the Router Appliance. This cost depends on the machine type you select, which determines the CPU, memory, and network bandwidth available. Higher performance machine types cost more, but provide greater throughput capacity. The second cost component is network egress charges. When traffic flows through the Router Appliance and exits to the internet or to other networks, standard Google Cloud egress charges apply. Traffic within the same region is typically free, but cross-region traffic incurs charges. The third cost component is licensing for the network virtual appliance software. If you use a partner solution, there may be bring your own license or pay-as-you-go licensing options. Custom images may have their own licensing requirements. The fourth cost component is network connectivity center charges. While there is no charge for creating hubs and spokes, data transfer through certain spoke types may incur charges. Read the NCC pricing page for current details. To optimize costs, right-size your Router Appliance virtual machines based on actual throughput requirements. Use committed use discounts for predictable workloads. Consider the traffic patterns in your deployment to minimize cross-region data transfer where possible. Cleanup commands. Let me provide the specific commands for cleaning up the sample configuration we built throughout this presentation. These commands remove all the resources in the correct order. The first set of commands removes the BGP peers from both cloud routers. For Cloud Router A, you run G-Cloud Compute Routers remove BGP peer twice, once for each peer. The peer name parameter identifies which peer to remove, and the region parameter specifies where the cloud router is located. You repeat this for Cloud Router B to remove its BGP peers as well. The second set of commands removes the cloud router interfaces. Again, you run the remove interface command for each interface on both cloud routers. The interface name parameter identifies which interface to remove. The third set of commands deletes the network connectivity center spokes. You use G-Cloud Network Connectivity Spokes Delete with the spoke name and region to remove spoke A and spoke B. The fourth command deletes the Network Connectivity Center hub using G-Cloud Network Connectivity Hubs Delete with the hub name. The fifth command deletes the Router Appliance virtual machine using G-Cloud Compute Instances Delete with the instance name and zone. Summary of key concepts. Let me summarize the key concepts we have covered in this presentation series on Network Connectivity Center with Router Appliance. Network Connectivity Center provides a hub and spoke architecture for managing network connectivity across Google CP and hybrid environments. The hub serves as the central management point, while spokes represent various connection types including VPN, Cloud Interconnect, and Router Appliance. Router Appliance enables you to bring your own network virtual appliance into Google Cloud. You install the appliance software on a compute engine virtual machine and use it as the backing resource for a network connectivity center spoke. This allows you to leverage familiar third-party solutions within the NCC framework. BGP is the foundation of route exchange between the cloud router and the Router Appliance. You configure BGP peers on the cloud router that reference the Router Appliance instance. The appliance must also be configured with corresponding BGP neighbors pointing to the cloud router interfaces. Multiple topology patterns are supported, including site-to-cloud connectivity for hybrid deployments, site to multiple VPCs for connecting on-premises to multiple Google CP networks. VPC-to-VPC connectivity for routing traffic between VPCs through a network appliance, and cross-region failover for high availability across geographic regions. Configuration Workflow Summary. Let me provide a summary of the complete configuration workflow we walked through. This workflow can serve as a checklist when deploying Router Appliance in your own environment. The workflow begins with prerequisites: creating or selecting a project, enabling billing, installing the G-Cloud CLI, and enabling the Network Connectivity API. Next, you create the VPC infrastructure. VPC networks with global dynamic routing mode, subnets in the appropriate regions, and firewall rules allowing BGP traffic on TCP port 179. Then, you create the Router Appliance virtual machine with multiple network interfaces, IP forwarding enabled, static IP addresses, and premium network tier. You install your chosen network virtual appliance image. After that, you create the Network Connectivity Center resources. First the hub, then the Router Appliance spokes referencing each interface of the Router Appliance virtual machine. Next, you create the cloud routers in each VPC network, add redundant interfaces to each cloud router, and configure BGP peers to establish sessions with the Router Appliance. Finally, you configure BGP on the Router Appliance itself using vendor-specific commands. Verify that BGP sessions are established, confirm routes are being exchanged, and test end-to-end connectivity. Thank you. In next steps, we have covered a comprehensive overview of Google Cloud Network Connectivity Center with Router Appliance. You now understand the concepts, architecture patterns, and step-by-step configuration procedures for deploying Router Appliance connectivity. For your next steps, I recommend reviewing the official Google CP documentation for the most current information and any updates to features or procedures. The documentation includes additional details on advanced scenarios, troubleshooting guides, and API references. Consider exploring the Network Connectivity Center Partners page to evaluate partner solutions that might fit your specific requirements. Partner solutions can simplify deployment and provide additional features tailored to particular use cases. If you are new to BGP, investing time in understanding BGP fundamentals will help you troubleshoot issues and optimize your routing configuration. BGP is a powerful protocol with many tuning options that can affect performance and convergence. Practice deploying Router Appliance in a test environment before implementing in production. This hands-on experience will help you understand the nuances and identify any organization-specific considerations. Thank you for your attendance. Please consider subscribing to the channel and liking this video.